All right, physicists, welcome to our March 19th edition of physics. Today we're going to be doing a bunch of review for our quiz, which you may have taken already, but be that as it may, we want to make sure that we're clear on everything. I do want to make one announcement at the beginning of this video, which is that your homework is not going to be due on Monday. It's going to be due on Wednesday. I think this homework was just a little bit too long to get done in the 1 week time, so I'll give you an extra 2 days, and hopefully that'll give us also just enough time to discuss everything we need to talk about. Okay, so a lot of review in this video, and hopefully some helpful pointers on how to succeed at your quiz and how to succeed at the homework. Okay, so we've talked a lot about the center of mass this week. And the center of mass for two particles, of course, is if you have one particle and another particle, you have the big M would be M1 plus M2. Okay, so let's say that we have a first particle and we have a second particle, M1 and M2, and they might be moving in different directions with like a V1 and a V2. They certainly have a position, R1 and R2, and I'm going to put vectors on all of these because these are all vector quantities. So if you wanted to find the center of mass, you would go ahead and go 1 over the combined mass times mass of the first times position of the first plus mass of the second times position of the second. Okay, so we've talked a lot about that. Of course, the reason I'm putting this as a r hat center of mass is that this works in the x, y, z, all of those directions. So for instance, if I wanted to find the x center of mass, I would do 1 over the total mass, mass 1 times x1 plus m2 times x2 for this particular two-body system. At the same time, I could also find out what the speed of the center of mass is by doing 1 over m, the mass 1 times the v1, m2 times v2. So this is the velocity vector for the mass going along with the first mass, the velocity vector going along with the second. And you can see that this is true because all I'm doing is I'm taking the derivative of both sides, the time derivative of both sides. The derivative of the velocity, or the position, is our velocity. Our derivative of velocity is going to be acceleration. So my A center of mass is going to be M1 A1 plus M2 A2, 1 over m. But if you notice what that is, if I multiply both sides by big M now, the total mass, it's just saying the MA, the mass times acceleration of my center of mass, looks like the sum of all of the MAs. The sum of all of, notice this is the total force on object 1. This is the total force on object 2 because F equals MA for net forces. So the center of mass is special. It looks like a particle. Let's see how that manifests in a couple of quiz questions for today. We're also going to be looking at using our momentum. This was our other idea from Monday. Momentum is mass times velocity, so momentum has a direction. Because F equals ma, that's our Newton's second law, we can also rewrite this in terms of momentum. So the net force on an object is proportional, or it actually is equal to how its momentum is changing. So if momentum is not changing in a particle, that means that we have no net force. That's just another way of saying that constant speed is what we're looking for. So staying still or constant speed, that means that you have no net force. If you do have a net force, it means that you're accelerating. Accelerating means changing speed. Okay, so nothing too new here, except that we can also now think about a total momentum of a system where we add together the momenta of all the different particles. So for instance, for that two-particle system that we were talking about before, the big P would be your P1 plus your P2, which would be mv1 plus mv2. And this v1 now is a vector, so it could have an xyz component. This has an xyz component. And I don't think we're quite going to get there today in this video, but where we'll go with that is that if you add up the momentum in the x direction, add up the momentum in the y direction, and you don't have any external forces coming into a system, what you'll have then is momentum conservation in every direction. Momentum conservation in the x direction, momentum conservation in the y and z direction, and okay, but we're getting ahead of ourselves. Let's do a simple example. This one's very much like a problem on your quiz today. And it says we have a bird, A. And we're just going to be worrying about the velocities, so it doesn't matter. I can put them anywhere. Bird A, there's A. He's got some mass A, 5 kilograms. And he's stationary. Okay, so the V of A in this two-dimensional plane is going to be 0, 0 meters per second. Okay, and it says bird B has a mass of 10 kilograms. And again, I'm not telling you where these birds are, so they could be anywhere. But he's moving due west at 7 meters per second. So 7 meters per second that way. I've done this as a north-south, east-west type of drawing. It asks, what is the velocity of the center of mass for this system of two birds? Well, let's look at what the formula said. This is our position of our center of mass. If I want to find my velocity of my center of mass, it will be 1 over the total mass of both birds times mass 1 velocity of times the velocity of bird 1 plus mass of, let me do this as A, and mass of bird B times velocity of bird B. Okay, so the total mass in this case is going to be 15 kilograms. So 10 plus 5. If I want to draw my VA as a vector, that would be 0, 0 meters per second. Whoops, I've already written that down. I need to rewrite that. Maybe I should worry about writing the velocity of B. Well, that's moving in the way I've set up the coordinates. It's going to be moving in the minus x direction, so minus 7, comma, and then it's not moving in the y direction, so it would be minus 7, comma 0 meters per second. And so if I wanted to set up this center of mass equation, what I would do is V center of mass equals 1 over 15 kilograms times mass of A times V of A. This is just 0, so this is 0, plus mass of B times V of B. This would be something like 10 kilograms times, and this is I and J, so let's say that this would be like minus 7I meters per second. And remember, the way that you do your vector algebra with this is you can just add your I components and add your J components, but we don't have any J components. And so our V center of mass in this case would be 10 over 15, so that's 2 over 3. It'd be minus 70 over 15. Whoops. and this should be kilograms and kilograms. Those cancel out, and so this will be meters. Oops, it'll have a direction I, meters per second. Or if you want to put it in a more natural language type of way, this would be 60 and then plus, so it'd be around 4.7 meters per second and going west. Okay, so that's the idea. A little tedious, but nothing too terribly tricky. It's all just keeping track of the language. Whoops. Okay. Here's another type of question that's on your quiz. It says the center of mass for a system containing two balls, one with a mass of 2 kilograms and the other with a mass of 4 kilograms, moves north at a constant rate of 5 meters per second. What is the net force acting on this system to keep it moving? Well, when I read this, it smells like flarf to me, because the net force acting on the system to keep it moving, you don't need a net force to keep you moving. Newton tells us that you keep moving whether or not you have a net force. What you need a net force is for acceleration. So in this case, if it's going north at a constant rate, the question is, what is its change in momentum? Constant rate means no change in momentum. So if your momentum is not changing with time, that's 0. And so your net force is 0 newtons. Done. Okay, so that's the whole, that's it. Done. All right. Now, the other idea we had was on Monday, and then we worked a little bit more on Wednesday with this idea, was the idea of impulse and momentum. And you'll remember the idea of work, where work was changing your kinetic energy, was you pushed on an object over a distance. So work is force times distance. Impulse, on the other hand, is force times time. So it has units of newtons times seconds. A newton is a kilogram meters per second squared times seconds. It has units then of kilograms, this second squared in the bottom. One of the seconds will cancel out, so it would be kilograms times meters per second. Notice that this is the same unit as momentum because it's mass times velocity. So what we found is that if you want to change the momentum of the particle, you apply an impulse. And if you want to make it go faster, you in the same direction that you're going, you apply an impulse in that direction. So if you're going in the plus x direction and you apply a plus impulse, you're going to make that particle go faster. If you have an object going in the plus direction, you apply a minus impulse, you're going to make it go slower or perhaps turn around. Okay? So I have a problem here that there's two ways that you could look at it. Now, on the one hand, this is a problem that you could have already done with our old methods, because it asks, a stone of mass m is dropped and falls freely under the influence of gravity, ignoring any effects of air resistance. Which one of the following expressions gives the momentum of the stone as a function of time t? The local acceleration due to gravity is g. That's your gravitational field strength. Now, in the old style, what you would have done is something like this. You would have said, okay, I'm going to set up my coordinate system where my y is pointing like this, and I'm going to use my kinematic equations and say that v equals at plus v naught. Okay, so my acceleration in this we're told is going to be g. So v equals g times t, and the initial speed is 0 because it says that it's dropped. It's falling from rest. So the v naught is 0. And so if you wanted to find what p is, p equals m times v, you could go ahead and say p equals mgt. Now, in physics, there's often many ways to get your answer. There are many paths that lead to enlightenment. So here's our new style. In our new style, we're going to calculate the impulse and say that it equals the change in momentum. Okay, so mv final minus mv initial is the force that I'm applying times the time. Now, my starting speed is 0. Okay, this is my final momentum. That's p. So let's just say p equals, the force in this case is mass times g, the gravitational field strength. So p equals mg t. Well, wouldn't you know? You get the same answer both ways. And I would like to argue that that's a feature, not a bug. You want to have self-consistent physics, and you have many ways of talking about the same things. So in our old style, we were just using kinematic equations. In our new style, we're using our impulse momentum theorem. Both the same, no contradiction. You know, 12 of one, or 6 of one, half dozen of another, blah, blah, blah. Okay, so the other thing that we figured out is that if you have a system that doesn't have any external forces, so the only forces acting are within the system itself, the special thing that happens is that the momentum of the system does not change. So the sum of all of your mv vectors gives you some constant in your x direction, in your y direction, in your z direction. And we said there's two different types of situations. One of them is called an elastic collision, and one is called an inelastic collision. And I want to give you, this is a little toy. It's called Newton's cradle, and here's an elastic collision, approximately. Now you'll notice, to a pretty good approximation, the speed that this one comes in at is the same as the speed that that one goes out at. Okay, so the kinetic energy of the system remains just about the same. And you know, there's a little bit of friction, and you can do this with 2 balls. And it's not as good because I'm just holding it, but you can also do it with 3 balls. All right, it's a cute toy. It's nice. All right, so this is the type of thing that I want you to think about in elastic collision, where the balls hit each other, they're very hard, they don't transfer any mass, they don't squish much, and the kinetic energy at the beginning is the same as the kinetic energy at the end. Now for an inelastic collision, the example that I used in class was a ballistic pendulum. That's where you shoot a gun and the ball comes off, it slides into something else, and it causes that object to go off. So that's a good example because in that process of the ball sticking into the other thing, there's friction. And the friction is going to dissipate some of the energy. There is not energy, there's not a conservation of kinetic energy in that case. There is, however, still conservation of momentum. So in both cases, momentum is conserved. In only one of the cases, kinetic energy is conserved. All right, so here's a conceptual refinement. It says 2 objects are involved in an elastic collision. Which one of the statements concerning this situation is false. Okay, let's read them. The total momentum is conserved. Seems okay. The magnitude of the force exerted by each object on the other object is equal. That's Newton's third law. Seems okay. The kinetic energy of each object is the same before and after the collision. That's not right. If you look here, this ball has a big kinetic energy, but when it collides, as soon as it collides, it stops moving. This ball gets the momentum is transferred over to this ball, and it gets the kinetic energy. Okay, so the kinetic energy of the system is conserved. The kinetic energy of each object is not. You don't end up just having all of the balls moving at the same speed. Okay, the total kinetic energy before the collision is equal to the total kinetic energy of the after the collision. Okay, and if you realize what we mean by that is you're adding up the 1/2 mv squared from all of the balls before and after. Total kinetic energy is conserved. I don't know how that's different, but it seems okay. All right, so here's a homework problem that has to do with this. It says you've got a mass A, a block A, mass 1.6, so your MA is 1.6 kilograms. It runs into a block B, so your mass B is 2.4 kilograms along a frictionless surface. The directions of the three velocities before and after the collisions are indicated. So you've got a VA initial, which is 5.5 meters per second. You got a VB initial, which is 2.5 meters per second. And you have a VA final, which is not known. That's what you're looking for. You have a VB final, which is 4.9 meters per second. So what happened here, MB is going like this. MA comes in really fast, and it sends VB going off fast, and drop my pen. And the VB now is going faster than it was before it got hit. The question is, does VA final, does VA go forward or backward? Okay, well, all you have to do is set up your equation. MA VA initial, that's the momentum of the first block at the beginning, plus MB VB initial equals MA VA final, that's the momentum of VA afterward, or of block A afterwards, plus MB VB final, that's the momentum of block B afterwards. Now, all of these variables you know, you can stick everything in there. All of this stuff you know, all you're doing is solving for this variable, VA final. Okay, and it asks what are the speed and direction? Well, the speed is just going to be the magnitude of that number. You're going to know whether it's positive or you're going to know what direction the block is going by whether that number is positive or negative. If it's positive, it's going to continue to go right. If it's negative, it's going to go left. All right. Now, the hard part here is asking the second question, is the collision elastic? Well, even if you know all of these things, you don't automatically know that. What you have to do is you have to calculate your initial kinetic energy. So 1/2 MA VA initial squared plus 1/2 MB VB initial squared. That's your initial kinetic energy, is the kinetic energy of the first block plus the kinetic energy of the second block. And then your kinetic energy final is going to be 1/2 MA VA final squared plus 1/2 MB VB final squared. Okay, so that's your final kinetic energy, your initial kinetic energy. Unless you've had some sort of explosion, you would expect your final kinetic energy to be smaller than or equal to your initial. Okay, so what you're checking in this problem is it smaller than the initial? Because then it would be inelastic. If it's equal to the initial kinetic energy, it's going to be elastic. So I'm going to let you check that out. All right, here's a good quiz type of momentum conservation problem. I like this problem. I didn't know if people would get it right before watching the today's video. So I left it off, but I think it's a great problem. It says you've got a rifle of mass m initially at rest. A bullet of mass little m is fired from the rifle with a velocity v relative to the ground. Which one of the following expressions gives the velocity of the rifle relative to the ground after the bullet is fired? Okay, so the key to realize here is that you have momentum conservation. So even though you have an explosion of some sort, the force on the bullet going that way is going to be the same as the force on the gun going the other way, and hence momentum is conserved. So clearly there's more kinetic energy at the end of this story than there was at the beginning, because at the beginning neither one of them is moving. There's an explosion, and then both of them have some kinetic energy. So what do we have? We have P before equals P after. So what momentum do we have before? They're not moving. 0 equals, now our P after is going to be mv, that's for your bullet, plus m gun, so they ask us to use a capital M for that, big M, v gun. Okay, so pretty easy. Now I can just go ahead and solve for this and find that v gun equals minus mv over big M. Okay, so I've got the momentum of the bullet, momentum of the gun, and my ultimate speed of my gun is going the opposite direction of my bullet with this speed. All right, beautiful, easy. I gave you a similar homework problem, just with a little bit of a kink in it. In this problem, you have a big motor and a little space vehicle. And the big motor has a mass that's 4m, and the space vehicle has a mass m. And the whole thing is stuck together at the beginning, and it's going with a speed v initial of 4,300 kilometers per hour. Now, in this case, these two unhook. So there's some sort of a spring mechanism. They go, or maybe it blows up, or who knows what happens. In any case, at this point, you have 4m, and it's going a bit slower because it's been knocked backwards. It's probably still going to be moving in the plus direction though, and this mass that's been knocked off is going to be going even faster than it was originally. Now they tell me that this is set backward with a speed of 82 kilometers per hour relative to the command module. So what that means is this V final is going to be 4,300 kilometers per hour minus 82 kilometers per hour. Okay, and then your V final of this extra thing So let's call this V final 1. V final 2, you don't know. You'd like to find it. Okay, but now you can just set up your momentum conservation, and it's easy. So here's your before. Here's your after. Momentum before equals momentum after. So you can set 5m, that's your total mass before, times V initial equals, so momentum before equals the momentum of your engine, or motor, I guess, your momentum of your motor plus your momentum of your command module. Okay, so momentum of your motor is going to be 4m times Vf1 plus m Vf2. Okay, this is mv for the motor, this is mv for the command module. Okay, and then all you have to do is solve for this. Okay, not too bad. I am confident you can do it. All right, now, as I've told you, there are combination problems that force us to use different paradigms for different parts of the problem. Like in this particular type of problem, it's a little bit special because you could use both momentum conservation and kinetic energy conservation are pretty much valid for this one. But usually, if you have like a bullet squishing into the block, you have momentum conservation in the part where there's some deformation of the object going on. You have energy conservation after that when you just have a transfer of the mechanical energy from kinetic energy into gravitational potential energy. So just to go through this problem explicitly, here's the example that I've given you as a homework. You've got a little mass m, and it starts out at some speed v that we don't know. And it barrels into our big mass m, which is 2 kilograms. So this is little m, that's big M. And it says the center of mass of the pendulum rises a vertical distance of 12 meters. 12 centimeters. Okay, so here, after this is all together, after that, you can start using energy conservation, and it goes up by some height of 0.12 meters. Okay, so for the first part of the problem, we're going to use momentum conservation. And let's call this V final. You would have little mv at the beginning, only the bullet has momentum, and then as soon as the bullet and the block merge, they have a final momentum that's going to be big M plus little m times V final. Okay, once that part of this is done, we start to think about energy conservation. In that case, we're going to have 1/2 this total mass, m plus m, V final squared, equals, and then it goes up to mgh. But the mass will be the total mass. So it'll be m plus m g h. And notice we're cheating a little bit here because we're assuming that all of this mass is just concentrated on the end. In a real lab experiment with this, you have got to be a little bit more careful about defining your center of mass being the place that has the change in mechanical energy. So that is a little subtlety, And it does matter to get the experimental results right. But let's not worry about it right now. Right now what we do is we go ahead and realize that those masses cancel out. We find our V final equals square root of 2g times h. Then I would feed that back in here, and I would find my V equals m plus m over little m times V final, square root of 2g h. Okay, so that's how I would calculate my bullet's initial speed. I know my mass of my block, my mass of my bullet. I know g that's just my 9.8 newtons per kilogram, and then h is this height of 0.12 meters. So there's a couple steps, but the problem itself is not that bad once you get into it. I gave you another ballistic homework problem that's not bad once you understand it. It's another one of these ones where there are no external forces. You just have the bullet and the block. The only slightly tricky thing is that you have a speed of a bullet before, so you get the mass of the bullet is 0.0052 kilograms, and it has an initial speed of 672 meters per second. And then that's your before situation. And then what happens is that the bullet rips through the block, goes all the way through. And now my bullet is going on the other way. It's going more slowly though. Now it still has the same mass, but its V is 428 meters per second. So whatever momentum it's lost, it has transferred to that block. Okay? So the momentum of this equals the momentum of that. This we also know the mass of it is 700 grams, so that's 0.700 kilograms. And there we go. So mv, the momentum of this before, plus 0, that doesn't have any momentum because it's not moving, equals mv of this. V, I don't know. That's what you want to find out. V of block plus mv of the bullet at the end. And m is, of course, the same, so there you go. So that's part A. Part B is a little trickier because it then asks, what is the speed of the bullet block center of mass? The thing to realize for this second part of the problem is that all of the forces here are internal. You don't have any external force, and hence the center of mass is not going to have a change in speed. Okay, there's no net force in this. The only forces that take place are the force pushing backwards on the bullet from the block, right there, and the force pushing forward on the, backward force from the block to the bullet, forward force from the bullet to the block, but they have to add together to be 0 because of Newton's third law. So in this particular case, the V of the center of mass is not going to change. It's just going to be 1 over the mass times m1 v1 plus m2 v2. And it turns out it does not matter whether you do that after the collision or before. So you could do it when the v is 0. That would be nice. That's a nice, easy way to do it. Or you could do it afterwards. And you can see that this has to be true because this is just the total momentum. And if the total momentum is the same before and after, this must be the same before and after. Okay, so today I ended class by having people watch this video. Essentially, the idea of this is that for you to have a rocket accelerate, it has to you have to have the forces from basically the paired forces from Newton's third law and momentum conservation. The ejected stuff going that way pushes the rocket forward this way. And so if you don't have stuff to push out of the butt of the rocket doesn't go forward. And in this video, he goes a little bit farther than what I just said there, to think about if you're standing on Earth, you actually have the total mass is still undergoing this force from gravity, and so he talks about how would you hover in the air, with this type of rocket idea. And so I encourage you to close out our day by looking at this video. I put a hyperlink in your PowerPoint, and I'm not going to spend this video time talking more about that. So what have we talked about today? System momentum remains constant unless there's a net force on the system, when it can change via F net, the force on all the particles added up, times m, the big mass of the whole system, times a of the center of mass. Okay. The second thing to realize is in our problems with a ballistic pendulum, for instance, energy and momentum conservation may be relevant for different parts of the problem. And then the last part is the one that I want to spend a little bit more time on Monday. And because of this last one, we didn't really have time to discuss it. You're going to go ahead and hold on to your homework on Monday, and we'll turn it in this coming Wednesday. All right, so please take the quiz today, and thank you for watching, and have a great weekend.